In this lesson, we will discuss the transpose of a matrix. Let's start from vectors. We already know that vectors are either rows or columns. So, let x be the column vector 1, 2, 3. There is a special operation which can turn it into a row vector. We can transpose it. Transposing the column vector 1, 2, 3 would yield in a row vector 1, 2, 3. We denote this operation with the letter t as a superscript. Therefore, x transposed, or the column vector 1, 2, 3 transposed, equals the row vector 1, 2, 3. Cool! Let's see another one. The row vector 1, 2, 3 transposed equals the column vector 1, 2, 3. So, this is a pretty neat operation. If we transpose x twice, we get x. How about another example? The row vector 2 minus 2, 0, 5, when transposed, becomes the column vector 2 minus 2, 0, 5. Very easy, right? However, there are several very important considerations here. First, when we transpose a vector, we are not losing any information. The values are not changing or transforming, only their position is. Second, transposing the same vector twice yields the initial vector. Third, our initial vector, 1, 2, 3, had a length of 3. In other words, it was a 3 by 1 matrix. By transposing it, it remained a vector of length 3, but it became a 1 by 3 matrix. This last consideration gives a peek into how transposing works for matrices. It turns all its rows into columns and vice versa. In terms of dimensions, when transposed, an m by n matrix becomes an n by m matrix. Let's check out an example, shall we? Here's the matrix A. 5, 12, 6 on the first row, and minus 3, 0, 14 on the second row. A transposed equals 5 minus 3 on the first row, 12, 0 on the second, and 6, 14 on the third. A is a 2 by 3 matrix. A transposed is a 3 by 2 matrix. We can see that the first column of A became the first row A transposed. The second column of A became the second row of A transposed. And the third column became the third row. This is how we transpose a matrix. The initial matrix A is nothing more than a collection of two row vectors, 5, 12, 6, and minus 3, 0, 14. Transposing the matrix A means transposing each of those vectors and putting them back together. So transposing matrices is nothing more than transposing a bunch of vectors. All right, let's get in Jupyter and see how this works out there. I'll first declare A as an NP array. In order to get the transpose of A, we simply write A dot capital T. That's all. Great! We will see two more examples just to solidify the knowledge. Taking the 2 by 2 matrix B containing 5, 3, minus 2, 4, and transposing it, we get another 2 by 2 matrix, this time 5, minus 2, 3, 4. Okay, finally, this 4 by 2 matrix, C, when transposed, equals that one. Again, notice that this operation is nothing more than transposing several vectors one by one. Right. Here are some further clarifications. Any scalar, when transposed, equals itself. Scalars are not the most interesting concepts, you see. So let's move on to vectors. We have the vector x equal to 1, 2, 3. Transposing it would yield the same result. That's because in Python, one-dimensional arrays don't really get transposed. Remember its shape? It is 3, comma. If I reshape it into a 3 by 1 matrix or a two-dimensional array, I will be able to transpose it though. That's another peculiarity you must consider when working with ND arrays in Python. Okay, great! In the next lecture, we will explore multiplication. Thanks for watching.